Okay, so today's last lecture covers a couple of situations involving, first of all, a plane mirror and then a mirror combination. So take a look at the third problem in today's lecture examples. It's the following. Show that a plane mirror obeys the mirror equation if the focal length is chosen properly. Okay, now let me draw a basic ray diagram for the plane mirror that is very similar to the other diagrams that you've seen already for the concave and convex mirror. Basically, let's draw a diagram where we find the focus. So to find the focus, remember what that entails, finding the image of a point object at infinity. So let's say that now right here is the plane mirror, completely flat surface. Right here is the optical axis that is perpendicular to it. And then for a point object at infinity, we have all the light rays coming in parallel to each other and parallel to the optical axis. That is like so. So how do each of these three light rays reflect? Well, notice that the angle of incidence for all three of these light rays is always 0 degrees. So then therefore the angle of reflection is 0 degrees and all these light rays just reflect upon each other like so. Notice that all the reflections are parallel. So they do not converge to a focus over here somewhere. They do not appear to diverge from a focus over here. So then therefore mathematically, what is the focal length? It's infinitely long. Here's another way to think of it. How large is the sphere if the surface of the sphere is perfectly flat? Well, the larger the sphere itself, the more flat the surface appears. So then therefore, if you're talking about a perfectly flat surface as you are for a plane mirror, this then means that the radius of curvature is infinitely long, or infinitely large. Therefore, the focal length is infinitely long as well. So there's a couple of different ways to think of why the focal length has to be infinity. Watch what happens now in the mirror equation. So in the mirror equation, I now have 1 over dO plus 1 over di is equal to 1 over f. However, 1 over infinity on the right-hand side of the expression is 0. Take this expression and solve it for di. So move this term here to the other side. And now take the reciprocal. Notice that the image distance is the same as the object distance, but it's negative. So recall the situation for plane mirrors in the previous folder for the last lecture from 2 days ago. So during one of those lectures, I described how the image of a plane mirror forms behind the plane mirror, and the image distance is the same as the object distance. That's this expression here. What does the negative sign mean, however? It means that the image is virtual. The image forms behind the mirror. Watch what happens now in the magnification expression. So we now have negative di over dO. Notice this simplifies to become positive 1. So you end up with an upright virtual image that's the same size as the object. Yeah, the plane mirror does obey the mirror equation as long as you get the focal length correct. That's kind of cute. Okay, and then lastly here, let's take a look at a mirror combination. Specifically, this is the reflecting telescope. Okay, before I go through my description here of the reflecting telescope and before we do a basic example, at this point go ahead and pause this video and take a look at my telescope demonstration video. Okay, now in my telescope demonstration video, I show you the two mirrors associated with a reflecting telescope, the parabolic concave mirror that is down at the bottom of the barrel of the telescope, and the secondary mirror which is positioned towards the top. As I briefly mentioned during the video, Isaac Newton was the person who invented the reflecting telescope. So on top of everything else that he did, just kind of like on the side, he also bothered to invent the reflecting telescope. The reflecting telescope has a number of advantages over what is referred to as the refracting telescope that we'll get to a little bit later on. For now, one of the big advantages associated with the parabolic concave mirror as the primary is that you can make it as wide as possible, and all of the weight is basically at the bottom of the telescope. This is not the case with a refracting telescope, which uses lenses. With a reflecting telescope, you could put a really heavy mirror at the bottom of the telescope, and then therefore it's easy to steer around. You want to make the mirror as wide as possible. You want to catch, if you will, as much light as possible. Because the more light that hits the telescope, the fainter the objects you can see, the greater the detail you can resolve in those objects, and then therefore the further all objects are away from you, you'll be able to see them as well. So this then means that when you make a telescope, a reflecting telescope, as large as possible, you can therefore see very great distances out into the universe, and then therefore back in time as well, due to the finite speed of light. Okay, now let's take a look at the one example that I've posted for you here involving the reflecting telescope. Okay, so we're going to do all of this for just a point object in infinity, say just using the telescope to look at a star. I'm not going to draw an extended object here. So a reflecting telescope consists of two mirrors. The primary mirror is a large parabolic concave mirror. There's no spherical aberration, with a focal length of 50 centimeters. The secondary mirror is a plane mirror that's positioned 25 centimeters in front of the primary. What we're going to do is calculate where the final image forms. We're also going to draw out the basic ray diagram associated with it. Once again, this is all for a point object at infinity. Okay, here's the basic idea. First of all, right here is the large primary mirror. This is at the bottom of the telescope. That's where all the weight is. Okay, and then right here is the optical axis like so. And we're given that the focal length here of the primary mirror, I'm going to call it F1, and it's given to us as positive 50 centimeters. So let's say that right here, for example, is the focus, F1. And then we take a look at a point object at infinity, so we look at a star. Now I'm just going to draw two light rays. One light ray up here, and then another light ray down here. And now what I'm going to do is apply the mirror equation. When I do, I have an object distance here, dO1. That's equal to infinity. The reason for that is because we're looking at a star that's infinitely far away. And now what I'm going to do is calculate the image distance for the first mirror. I'm going to call it di1. So let's just follow the math. So 1 over infinity plus 1 over di1 is equal to 1 over f1. This right here is equal to 0. This right here is 50 centimeters. Therefore, di1 is positive 50 centimeters. This then means that the image forms here at the focus. We already knew that, but I'm calculating it here directly by using the mirror equation. So now let me go ahead and start to reflect the light rays. When I do, however, they're not going to reach the focus. And the reason why is because the secondary mirror is positioned in between the primary focus and the parabolic primary mirror itself. The secondary mirror is positioned right here. Now in this particular design, I'm positioning the secondary mirror, a plane mirror like so. This then means that when these light rays here and here strike this mirror eventually, they're going to reflect off in this direction. That's not quite the design that I have in my telescope, which is called a Newtonian reflector. In a Newtonian reflector, we take the plane mirror here and we tilt it at a 45-degree angle. That then redirects the light rays down to the side in this direction. That's where you then put your eyepiece. The eyepiece itself, by the way, is what is called a double convex lens that then focuses the image into your eyes. However, in this design, we're going to go ahead and we're going to place the plane mirror like so. This design right here, by the way, it's called a Schmidt-Cassegrain telescope, as opposed to Newtonian. Okay, now, let me go ahead and reflect these light rays off the primary mirror. They reflect towards this focus, like so. and then like so. But they don't quite get there because this mirror now is in the way. Okay, now this is a plane mirror, so then therefore it has an infinite focal length. So the focal length, f2, is given to us as infinity. It says that the secondary mirror is positioned like so, 25 centimeters in front of the primary mirror. Now watch this. This right here is also 25 centimeters, but this is now the object distance for the second mirror. The reason why is because it looks like these two light rays, ignore the arrows, just look at the lines themselves. These two light rays look like they're coming from back here. This is where the image of the first mirror forms. Therefore, the image for the first mirror becomes the object for the second mirror. And notice that this object is behind the second mirror. Therefore, I have to make the object distance negative for that reason. That's how the sign convention works. Once again, this distance right here, the object distance for the second mirror, is 25 centimeters, but we make it a negative number. So now DO2 is negative 25 centimeters. And now we just follow the math to find the final image distance, DI2. So we have 1 over DO2 plus 1 over DI2 is equal to 1 over F2. This right here, infinity, 1 over infinity is equal to 0. Move this to the other side. It becomes positive. Take the reciprocal. DI2 is positive 25 centimeters. The positive sign here means that the final image forms in front of the second mirror, which is over here, 25 centimeters in front of it. This right here is where the final image forms. So then therefore these two red light rays that we've been following in this process reflect to here and here. And then therefore right here is where the final image forms. So in this particular design called a Schmidt-Cassegrain, well, there's actually a hole here in the primary mirror, and this right here is where you position your eyepiece, your camera, or whatever it is, like so. So that's that type of a design for a reflector telescope, okay? Okay, this concludes right here today's series of lectures. Today's shirt was Ritual Necromancy.